We've got a stack of sources today that, at first glance, they look like they belong in some kind of super dry manufacturer's technical manual.
Oh, absolutely.
We're talking supply chain logistics, parts diagrams, heavy industrial maintenance protocols. But when you actually dig into this stuff, it reveals itself as this brilliant strategy guide for risk mitigation
Yeah.
in really high-stakes environments.
It's a classic case of hidden wisdom, isn't it? We're dissecting briefing material that was really written for procurement officers, for fleet ops managers, and safety directors in the heaviest sectors.
Right.
So think massive earth movers in mining, global oil and gas infrastructure, that kind of thing. And the core, almost counterintuitive lesson here is that the uptime of a billion-dollar fleet often comes down to mastering what the sources call precision procurement.
And the focal point of this entire mission, the component that kind of serves as the object lesson here, is one very specific, very small pipe. The Caterpillar Turbocharger Drain Line. We're looking at components like the 379-68026. And if you're just looking at a price sheet, this just looks like a commodity, a cheap piece of bent metal tubing.
Precisely. And that's the trap these sources want you to avoid. The mission isn't just to talk about inventory management. It's to fundamentally shift how you view this part.
How so?
Well, the sources argue that buying a certified drain line transforms an unpredictable, potentially catastrophic operational risk into a manageable, predictable line item. You aren't buying a pipe.
You're buying insurance.
You are buying insurance,
Yeah.
Exactly. This simple drain line, it's often hidden from view, but it functions as this critical piece of the financial and safety puzzle. We have to stop seeing it as just a consumable.
And start seeing it as what it is, the linchpin of system failure protection.
That's it.
So why should a procurement manager, someone whose job is usually to save money, why should they suddenly care so deeply about this specific piece of tubing that probably costs less than a good cup of coffee?
Because our sources highlight this phrase, the quiet terror that happens the second this part fails.
And what does that look like?
The stakes are they're truly wild.
Huh.
When we talk about an oil leak from a turbocharger in these heavy applications, we're talking about an immediate, uncontained escalation. It doesn't, slowly drip for a week.
This is sudden.
Oh, yeah. The functional consequence is swift engine deterioration. You got the visible cues like sudden excessive smoke just pouring out of the stacks, a very public indicator of a really serious internal crisis.
And once that happens, what's the damage inside the engine?
The primary destruction is, it's just so rapid. The turbo seals fail, the oil pressure drops or spikes, and you start suffering irreparable damage to the high-speed bearings in the turbo assembly itself.
Wow.
And the result is an immediate and often mandatory emergency shutdown. Imagine a key compressor station or a massive mining shovel just going offline, suddenly.
That failure isn't just an inconvenience. In that world, that's a multi-million-dollar event in, minutes?
Absolutely. The sources are very specific on this. When you're running a major oil drilling operation or a 247 power plant, the hourly rate for unscheduled downtime can easily exceed the cost of the engine itself over a few days. We're talking massive production losses.
And it doesn't stop there, I assume.
Not at all. This is also where the regulatory hammer drops.
Environmental tickets and fines.
Exactly. An uncontained oil leak, especially one that's causing visible smoke, that triggers compliance failures. You're looking at regulatory fines, environmental cleanup costs, which they easily eclipse the maintenance bill.
The scale of that is hard to grasp.
It is. One source noted that in some jurisdictions, the penalties and mandatory remediation costs from a single high-profile environmental incident can cost more in a single hour than many smaller businesses spend in an entire month.
That is the financial risk that starts at the end of a tiny drain pipe. It's an incredible lesson.
It really is.
The cheapest part on the engine can trigger the most expensive consequence. If the failure is that immediate and that expensive, then we have to look under the hood. We have to understand exactly how this pipe is supposed to work and why it's so critical.
Right. So the entire system centers around the turbocharger, which is, it's an engineering marvel. It spins at phenomenal speeds. We're talking tens of thousands of revolutions per minute, and it operates at extreme temperatures because it's right next to the exhaust.
Okay, so to keep this thing alive, it needs a constant deluge of lubrication.
A constant deluge, that's a great way to put it. That oil is flowing in under immense pressure to lubricate those high-speed bearings.
And that's where the drain line comes in.
Correct. And this brings us to the drain line, which the source material identifies as and this is their term, the critical fail point. The oil has done its job, And now it needs to get out of the turbo housing quickly and efficiently back to the sump to be cooled and filtered.
Okay, hold on a minute. If it's just returning oil to the sump, why can't we just use some heavy-duty flexible tubing? Or just a cheaper, simple length of metal pipe cut to fit? I mean, that's what a quick fix mentality might suggest, right?
See, and that is the crucial misunderstanding. It's not just an exit hole. It's a piece of calculated fluid engineering. The drain line's job is to ensure zero back pressure.
Okay, explain that.
Think of it like a kitchen sink drain. The faucet is running full blast, that's your pressurized oil feed. And if the drain pipe is clogged or kinked or just too small, the sink, which is the turbo housing, it backs up immediately.
And in this high-pressure environment, that backup is catastrophic.
Absolutely. If that oil can't drain out fast enough, pressure builds up against those really delicate internal turbo seals. Those seals are engineered for minimal friction, not for resisting high internal oil pressure.
And so that pressure just blows them out.
It blows out or damages the seals, leading to the rapid loss of oil and, well, the subsequent destruction of the bearings.
That makes the rigidity and the precise specifications of the OEM part make a lot more sense. It's about maintaining flow tolerance and a very specific bend radius.
Precisely. These certified components, like the part number we started with, the 3796026, or others they reference, like the 3499188, are designed for highly specific flow dynamics. The internal diameter, the coating materials, the precise length, the bend radii.
It's all engineered.
It's all engineered to handle that continuous, high-volume, high-temperature oil flow without any turbulence or restriction. A substitution, even one that looks close, often compromises one of those subtle engineering specs.
And it turns a reliable exit into a throttling bottleneck.
You got it.
So we have this tiny, precision-engineered part that is constantly battling heat, pressure, and flow dynamics.
Yeah.
We need to know how the field teams can predict failure rather than just reacting to the smoking engine.
And the sources provide some genuinely actionable intelligence here. They dissect 4 primary ways these critical lines fail. First, you have the mechanical issues, often tied to installation or maybe environmental debris. So, clogged returns from sludge or carbon buildup impeding the flow, and improper routing.
Improper routing sounds like such a simple mistake, but that goes right back to the flow dynamics you were talking about, right?
It does. Installing a line with an unintended kink or, forcing a slightly wrong-fitting pipe creates an immediate flow restriction. That's instant back pressure and seal risk.
But I'm guessing there are more insidious failures.
There are the ones caused by the engine environment itself.
Which would be?
Thermal fatigue and corrosion. The drain line is right next to the scorching hot turbo housing. It cycles constantly between extreme operational temperature and a cold shutdown. This constant, brutal heating and cooling stresses the material science of the pipe itself.
It's like bending a paperclip back and forth until it just breaks.
That is an excellent analogy. And then you have corrosion, which degrades the material, leading to these small pinhole leaks that quickly expand under pressure. A leak here means you're losing the necessary flow rate, damaging the environment, and potentially causing a rapid system shutdown.
So if I'm a safety officer or a maintenance foreman walking around during a routine inspection, what are the concrete visual cues I should be looking for to spot a line that's about to blow?
This is how we move from reactive firefighting to prediction. Maintenance teams need to be trained to look for 3 things. First, any sign of kinking or scraping that suggests improper routing or contact with other components.
Okay, that's straightforward.
Second, look for visual evidence of thermal stress. So, excessive discoloration or carbon buildup that suggests the metal has been chronically overheated beyond its operational tolerance.
And the third?
Third, and this is the most crucial, look for the earliest signs of oil residue. Even a fine weeping or just a dusting of oil residue on the outside of the pipe. That residue is the first physical sign of degradation and corrosion that comes before a catastrophic failure.
And replacing that weeping line with a certified component during scheduled maintenance
Is a measurable uptime gain. That shifts the risk management completely. Instead of waiting for a siren, you're looking for a subtle change in color.
We've established the engineering problem. Now we need to move to the management solution. If this drain line is truly risk insurance, how does a director of procurement structure their strategy to build that necessary redundancy without, causing massive inventory bloat that makes the CFO panic?
This is where procurement stops being just transactional and becomes strategically critical, and you have to address that CFO panic head on. The two key pillars of the solution in the source material are inventory strategy and specification discipline.
Okay, let's start with inventory. My inner CFO is screaming right now. You
Yeah.
want me to tie up cash on a shelf by wholesale stocking $10 pipes that might not be used for a year?
And that is the legitimate cost concern. That's why the strategy isn't blind hoarding, it's rationalization. The source material emphasizes aligning the stock of critical fail point spares, like the 379-6026 with scheduled maintenance windows.
Oh,
The goal is to always have the certified part on hand when a planned engine overhaul or inspection requires a replacement. You eliminate the emergency scenario entirely.
so you budget for the replacement as part of the normal service cycle, not as a panic purchase.
Exactly. And the strategy has to be dynamic. A fleet manager on the Gulf Coast in a corrosive, humid environment needs to stock a higher volume of these lines than one operating a dry land fleet in, say, Nevada.
Because of the increased risk of external degradation.
Right. Strategic stocking means putting the spares where the environmental risk is highest and anticipating the replacement frequency.
And the second pillar, specification discipline.
That is the guardrail against cost cutting that undermines reliability. Procurement must have absolute discipline in confirming the correct fitment and the traceability of the component. The moment you start sourcing alternatives that lack the certified engineering, you lose the guarantee that the component can withstand the thermal fatigue and provide the necessary flow management.
Okay, so let's talk about the wholesale cost math that the sources detail. How do you actually measure the benefit of that strategic stock?
The math is brutal, but it's clear. You compare the wholesale cost of stocking a certified part, which is minimal, against the true cost of an emergency procurement. An emergency means paying exorbitant premiums, expedited shipping that may or may not arrive on time, and just the chaos of diverting labor hours to chase a single component.
So you're not saving $5 on a part.
No. When you stock certified Caterpillar components, you gain measurable, predictable uptime that far outweighs that small unit cost. You are investing in preventing the $50,000 hourly loss.
Which means procurement is actively contributing to the measurable health of the company's P&L, not just being a cost center.
That's the pivot. This strategic approach, viewing the component as risk management, it drives benefits across the entire operation.
For compliance and audits, what does this proactive component management look like?
It cleans up regulatory audits significantly. Using genuine, traceable components is documented proof to regulators and, critically, to your insurance carriers that you are actively managing your major operational risks.
And I imagine insurance carriers love that kind of data.
They love reliability data. They view this systematic approach to critical components very favorably. It often translates into better terms.
And we can't overlook the human element, the safety for the crew.
Undeniable. Properly routed OEM-quality drain lines reduce the probability of high-pressure oil leaks, which are significant environmental and safety hazards for the maintenance crews working on the equipment.
Right. Less unexpected oil spray means fewer slips, less exposure, and just cleaner work areas.
Exactly. So this is a proven methodology for parts rationalization. It ensures your stock optimization aligns with predictive, scheduled maintenance. It moves the entire operation beyond the chaos of emergency stops.
So the goal is to build resilience and redundancy into the systems that need it most.
It is. We started with a specific part, the 379-6026, and confirmed that mastering the procurement of this tiny component is literally the difference between smooth operations and an unplanned multi-million-dollar disaster.
Reliability isn't built on the biggest, most expensive components. It's built on the mastery of the hidden, critical details. We've established that the cost of an hour of downtime in heavy industry is just astronomical. If we adopt this mindset and view the certified drain line as necessary risk insurance rather than an expense, it raises a final, really vital question for you to mull over.
What is the true long-term operational cost? And that includes downtime penalties, subsequent component damage to engine seals, compliance fees, of trying to source the cheapest possible alternative to a certified component that's designed specifically to protect flow and control system integrity. Where else in your operational systems are you currently buying what you label a consumable, when in reality you should be strategically investing in risk management?